E può ripetere quello che ha detto prima della pausa sull'effetto tunnel?
Sì, ok. Ehm, vado in inglese, così. Okay, there was a comment request concerning the tunneling effect comment that I presented to you before the break. So the idea is the following. If we use the diagram where on the vertical axis there is the energy, and on the horizontal axis we have the position, and we display in this diagram the position of all the ions, the potential, the solid, let's say, the solid state potential has more or less this structure. So the idea is, if you consider the electronic levels to be atomic levels, in the atomic picture, you may represent the levels as, let's say, corresponding to specific energies on the vertical axis. So if the atomic level has no perturbation when you switch from the atomic picture to the solid state picture, then the energy is the same. If the levels are, let's say, different in the two cases, then you have that, for instance, the energy is not exactly this one here, but you have, let's say, the degeneracy removal as we saw before. Irrespective of that, then you have the same situation on all the ions of the lattice. So tunneling effect means that if you pick up one electron here, for instance, in this ion, then, for instance, you apply a voltage or something that tries to, let's say, move the electron. In principle, the electron is not free to move in space because there is an energy barrier here that it has to overcome to jump on the second, on the next neighbor, second neighbor, and so on. So the tunneling effect can be seen as the capability of the electron to jump this barrier and to reach the next neighbor. And then the electron will be able to make another jump, and so on through the solid, so the electron may propagate through the solid. The comment before was concerning the fact that when one electron jumps, if you want, the probability to have this tunneling effect is related to the superposition between the atomic wave functions on the electron on the first ion and the electron on the second ion, considering also the contribution of the perturbation. So that gamma is a sort of is related to the probability for this tunneling mechanism to appear, to be observed. The only thing that we miss using the tight binding approach is the fact that when the electron jumps from this place, from this position to the next to the position of the next ion, then to, let's say, to reach one of the levels here, one of those levels, the electron has also to overcome the Coulombian repulsion that the electron feels with respect to all the electrons that are found at this side. So that's why at some point you do not have this smooth continuous transition between velocity difference from 0 down to velocity equal to 0, because that is observed only if the tunneling probability can be switched continuously from a non-zero value to the 0 value. But in the calculation of the tunneling probability, we didn't consider the fact that you have also Coulombian repulsion. So at some point, that probability drops to 0 because the Coulombian repulsion is stronger when the tunneling probability decreases, and at some point, let's say the Coulombian repulsion wins over the tunneling probability, and so the electron is not able to jump over the barrier. So that was the, I had this in mind when I made the comment concerning the tunneling effect. Is this clear now, or is there some point that has to be discussed in a better way?
Yeah, it's clear enough. Thank you.
Okay. And now the second comment concerning the mistake that I made before. And just to write things more in maniera più compatta in italiano. The idea was to evaluate this integral. So this was the integral, and so this is just the Schrödinger equation. Then we make the scalar product with one of the atomic wave functions. If we want to rewrite that in a more compact way, we may write that as phi of n So we may write that in this way. If I split the second term in two parts, then I have phi of n atomic psi of k plus phi of n perturbation psi of k is equal to E of k phi of n psi of k. What I missed before was the fact that the Hamiltonian is a self-adjoint operator. So you may apply that on the right side, or you may also apply that to the left side. So if in this case you apply the operator not to psi on the right, but to the atomic orbital on the left, then the energy is real. So even if you consider the complex conjugate, you always have the energy of the level. So what is left here is E of n, and then phi of n scalar product psi of k plus phi of n perturbation psi of k, and this is equal to E of k phi of n scalar product psi of k. So due to that, you have these two terms that are exactly the same apart from the energy, the coefficient of the energy. And so due to that, you may write E of n minus E of k. Then you have the scalar product phi of n psi of k plus phi of n perturbation psi of k, and this should be equal to 0. Then this integral and also this integral can be split into the two contributions r equal to 0 plus summation over all the values with r different from 0. So then from now on, the calculation proceeds as before, but the difference is that now we have that this coefficient, the difference of the energies, is in front of both the terms corresponding to r equal to 0 and the term corresponding to r different from 0. But in my calculation before, that was just in front of one of those terms because I forgot to exploit the fact that the Hamiltonian operator is self-adjoint, and I just applied the Hamiltonian operator on the psi of k to the right and not to the atomic orbital to the left. So I made the wrong application of the Hamiltonian. So instead of applying the Hamiltonian to the left, I applied that to the right. So at that point, I found different two terms that had not this difference of the energies in front of those. So that was the point. So that was why at the end, I had not the 1 plus alpha at the denominator, because I had not two terms with the same energy coefficient in front. Is it fine for you, or do you want me to do some more steps just to, let's say, join in easier way the previous calculation. Is this fine also for those that are connected? So from now on, it's clear how to proceed, or do you want some more steps? Okay. Okay, so that was the... Okay, thank you. Yeah, so what I would like to do now is just to make an exercise using the time-binding model to consider what happens in a, let's say, not a real system, but in a specific case, because making this exercise, I wanted to stress some of the details concerning this model and also the representation of the band structure that you have, that you may evaluate during an exercise or a calculation. Due to the fact that it is almost 10 past 11, I think that I will not be able to conclude the exercise, so I will conclude that tomorrow morning. And the idea of the exercise is the following. So the idea is to apply the tight binding model in case you have a cubic crystal. So we consider a system with a cubic symmetry, just a simple cubic lattice. And in this case, the let's say, I prefer not to give you all the questions now, just because some of the questions require additional comments. So I just start with the first question, and then I make the comments concerning that question, and then I go on with the other questions. The first step is describe the energy versus wave vector dependence when K is close to 0. So when we are close to the center of the first Brillouin zone. As we saw before, the energy versus wave vector dependence in general for the tight binding approach is equal to the energy of the level in the atomic case. Here I make reference to the S level situation. So this is just something that starts from the S picture that I used before. Then before we had plus beta. And just to, let's say, if you remember the example that I made before, the energy at the center was higher than the energy at the border. And that was due to the fact that gamma was positive. Just to remove that problem, I here change the sign. Just in this exercise, I change the sign in front of gamma. So I set a minus sign in front of gamma. So we have the usual fact that this energy at the center is the lowest energy, and the energy at the border is the highest, has the highest value. So now, for this motivation, I write minus, not plus as I did before, the summation over the next neighbors, gamma of r e to the I k r. So this is the starting point, and will be the starting point also for all the other questions later or tomorrow morning. At this point, the idea is, if we are interested in seeing what happens when k is close to 0, we just write the full expression for the energy, making the switch to the cosines as we did before, and then we make an expansion of the cosine for k close to 0, so to have an expansion of the energy for small values of the wave vector. So in general, E of k is E of s plus beta. Then we have the minus gamma. And who is R? R is the vector that joins the origin with the first neighbor. In this case, if we have a simple cubic lattice, and the lattice spacing of this cubic lattice is equal to A, then R in this case, the modulus of R, sorry, in this case is A. So I write gamma of A to stress the fact that we evaluate gamma just at the first neighbor. And then we have the phases. So I have e to the I, k, I. So my first neighbor to the right along the x direction, just to distinguish the three components of the k vector, I write kx. Then I have e to the minus I kx a. And the same for y and z. So we have three couples of two phases, and in each case, we may replace the phase with twice the cosine of kxa or kya or kza. So this is es plus beta minus gamma of a. I take the two factor out of the parentheses. So I have cosine of kxa plus cosine of kya plus the cosine of kza. So this is just a rewriting of the initial equation. So this is valid for any arbitrary vector of k, any value, sorry, of k. What happens now if we consider the k close to zero expansion? Each cosine can be written for small values of x as 1 minus x squared divided by 2. So if k modulus is close to 0, I may rewrite this as es plus beta minus twice gamma of a times 1 minus kx divided by times a divided by 2 squared plus 1 minus ky a to the power of 2 divided by 2 plus 1 minus kz a squared divided by 2. So this is the low k expansion. And so we have es plus beta. Then we have 3 times 1 within the parentheses. So we have a minus 6 gamma of a, another constant. Then we have that the 2 of the 2 gamma may be simplified with the 2 below the power of 2 that we have within the parentheses. So we have plus gamma of a that multiplies kxa squared plus kya squared plus kza squared. This can be written also as es plus beta minus 6 times gamma of a plus gamma of a times a squared times k squared. So in place of writing the square of k as a sum of the square of the components, I just write square of k. So I just summarize kx squared, ky squared, and kz squared into k squared. This is equal to, let's say, E0, a constant, where E0 is Es plus beta minus 6 times gamma, so this is just the constant value, plus gamma of a squared, k squared. So we have that for small values of the k vector, of the wave vector, the energy dependence is parabolic with respect to k. So this can be rewritten as let's say h bar squared divided by twice the effective mass times k squared. So let's say there is not a physical motivation behind this. So there is not a physical motivation that forces me to rewrite the things in this way. But in general, when we see a quadratic dependence of the energy as a function of the wave vector, we think about the free electron problem. So it is possible to rewrite the things in this way just to restate the problem in terms of the free electron one. Because until the dependence is parabolic, then everything we know concerning the free electron model can be applied to this specific case, even if the starting point was not the one concerning the free electron picture, because we started from the tight binding approach in this case. And to be, let's say, to make this assumption, we have to say that gamma of a squared is equal to h squared divided by twice the effective mass of the electron. So at this point, we may evaluate the effective mass of the electron, and the effective mass is equal to h bar squared divided by twice gamma a squared. And please note that this is, let's say, not important in general, but important as a way to display something. If you note, gamma is at the denominator. When the overlap is small, gamma is small. So small overlap means small value of the overlap integral gamma. Due to the fact that the effective mass is inversely proportional to the value of the overlap integral gamma, when gamma goes to 0, the effective mass goes to infinity. So in the free electron picture, you may say that, sorry, one step back. We are using the tight binding approach. In the tight binding approach, we have seen that when k is close to 0, the energy dependence is similar to the free electron one. But to have this similarity, we have to redefine the rest mass of the electron to be equal to an effective value. That is this one here. And we have gamma the denominator. When in the tight binding approach, you have the, let's say, contribution of the overlap that goes to 0, in this effective free electron picture, the mass of the electron goes to infinity. So it's just like as if when the probability to make a jump, the tunnel effect from ion to ion goes to 0, then the equivalent is, in the tight binding language, that the velocity has to drop to 0. In this effective picture, the language is the mass of the electron has to go to infinity, because otherwise, if you apply a force, the electron has to move. So a way to, let's say, to impede the electron to follow a possible external force is, in this effective picture, to have an infinite mass, because in that case, the acceleration of the electron drops to 0, so any arbitrary force is not able to move the electron. So that is an important, I wanted to stress that, as when I presented to you the free electron models, I told you if it may happen that the free electron model, the free electron picture is actually the right picture for the system, and so we may go on with the free electron model. But it may also happen that the system behaves as if the free electron model was fine, but we have to redefine some constants. And this is one of the cases. So in this case, at this point, from now on, everything we know from the Sommerfeld model can be applied in this situation, apart from the redefinition of the electronic mass. So if our aim is to study what is the behavior of an electron that is close to the center of the first Brillouin zone, then we may forget the tight binding approach, just use the free electron picture only after having redefined the rest mass of the electron to be equal to the effective mass of that. So from now on, just with this new definition of the electronic mass, we may again find the conductivity properties or the resistivity of the system, to study the optical properties, whatever, just redefining the rest mass, the effective mass of the electron. Okay, and let's say tomorrow morning, I will conclude just by investigating not just what happens at the center of the zone, but also what happens when we reach the border of the first Brillouin zone. Okay, other questions or comments? Okay, so I switch off the registration